Operation of functions. Let's say that we have two functions. One of them we'll call f of x, the other one we'll call g of x. So if we want to operate on functions, and using the basic operations of addition, subtraction, multiplication, and division, it's pretty intuitive. F plus g of x, written this way, is simply just f of x plus g of x. And since these functions are defined by either polynomials, rational expressions, radicals, all of those algebra rules are going to apply. Subtraction basically works the same way. F minus g of x, sorry about that, is equal to f of x minus g of x. All right, again, it works the way your intuition kind of tells you. Multiplication, fg of x, again, you're not going to really see a multiplication symbol. Sometimes you'll see a star or something like that, but fg implies multiplication. So that's going to be f of x times g of x. And then we have f divided by g, which is written as a fraction, as f over g. And that's f of x over g of x. And it can be reversed, and then you can put g on top and f on bottom. So what we're doing here is making brand new functions, right? F plus g of x is a brand new function, which is comprised of f of x plus g of x. And whatever the new function is, it's going to have a potentially a new domain. And over here, basically, the domain of the new function must meet the domains of the old functions and the domain of the new function. So when you do potentially maybe multiply two functions together, then you're going to have to meet the domains of f and g individually and whatever f times g turns out to be. Okay, and again, following all the rules of domains and things like that we did last class. Be careful again with f divided by g. Notice that this is now making a rational function. So we do have to keep track of those rules. So let's work on some of the some of the operations first, right? Something like f plus g. So here we have f of x defined as 5x plus 9. We have g of x defined as x squared minus 6x minus 10. So if we were to evaluate, let's say, f plus g of x, then we would simply be adding 5x plus 9 plus x squared minus 6x minus 10. Right, it's really just at this point, combining like terms, right? Just algebra, combine like terms here, and we're going to get x squared. Let's erase that. Ooh, that's too big. Let's say x squared minus x minus 1. Okay. And this would be the new function. Once again, the domain, it's not asking for us, but let's discuss it anyway. The domain of f plus g is going to have a negative infinity to positive infinity domain because it's a rational function. And the originals are polynomials too, 5x plus 9, x squared minus 6x minus 10. So in this case, everything works and it's all good. But again, that's something to be aware of. Let's say g minus f of 8, right? So we can do two separate things here. One, we can evaluate g minus f of x and then plug 8 into there. But we can also just evaluate g of 8 minus f of 8. All right, there's two things to do here. Both of them will yield the same results. So let's take x squared minus 6x minus 10, which is g of x, and let's subtract out 5x plus 9. Right, and subtracting these two polynomials requires that we distribute this minus sign to get x squared minus 6x minus 10 minus 5x minus 9. Now we can combine like terms. Let's underline some of these like terms. Negative 6x minus 5x, negative 10 minus 9. So we're going to get here x squared looks like a minus 11x, and then it looks like a minus 19. So what we have here is g minus f of x. And then we can plug the number 8 into here because this one is saying that the input has to be the number 8. So we'll get 8 squared minus 11 times 8 minus 19, which is going to work out to be negative 43 after we add all that and subtract all that together. Moving down to part C, let's look at f times g. Again, we're taking 5x minus 9. Oh, sorry, that's a 5x plus 9. That's f of x. Multiplying it to x squared minus 6x minus 10. All right, so the name of the game here is distribution. We are first going to distribute this 5x into x squared minus 6x minus 10. Right, it's not exactly FOIL. It's a little bit larger than that. So we'll get 5x to the third minus 30x squared minus 50x. And that is what we get when we distribute 5x into each and multiply each of those. Now we're going to take this plus 9 and distribute it into x squared minus 6x minus 10. So get ourselves a plus 9x squared minus 54x minus 90. And then we can combine like terms. Let's take a look. Let's see, negative 30x squared plus 9x squared. X to the first over here are going to combine as well. So 5x to the third minus 21x squared, looking like we negative 30 plus 9. And then negative 104x, combining those x's together, minus 90. And because this is just a general x, we don't need to add a separate input in there, and this is our answer. So let's look at here at f over g. Simply taking f of x, which is 5x plus 9, and putting it over x squared minus 6x minus 10, which is g of x. And if this simplifies, then we would do so, but since 5x plus 9 doesn't factor, that means this doesn't simplify. So these are examples of all four operations we can do to a pair of functions, right? Again, we can take the general x input, or we can put our own input in with numbers and evaluate them. But remember, when we are using actual inputs, we do have to adhere to the domains that are given to us. In this case, A, B, and C domain is negative infinity to positive infinity. Again, the same as what we're starting with. But remember, for part D, we're making now a rational function. And that is going to have a different domain. Not based on these, but based on now that x squared minus 6x minus 10 is the denominator, it cannot equal 0. So let's take a look at something a little more complicated, and we will look at the domain of this function here. All right, let's look at h of x being radical 7x plus 2. Let's look at g of x being 1 over x squared minus 5x plus 6. And the first thing we want to find here is h plus g of x. Right, so this gets slightly complicated, but nothing we haven't seen before, because since h of x is a radical, 7x plus 2, and we are adding this to g of x, x squared minus 5x plus 6 on the denominator, and then 1 on the numerator. Now we are adding rational expressions together, which means we're going to have 7x plus 2, the square root of that, over 1, plus 1 over x squared minus 5x plus 6. Now, since we are adding rational expressions together, then what we do need is a least common denominator, and that LCD is going to equal the only denominator that we have, x squared minus 5x plus 6. So that means we're going to need to multiply that on the top and the bottom of this first fraction in order to make the denominators match. So x squared minus 5x plus 6 times radical 7x plus 2 divided by x squared minus 5x plus 6, and this is going to be plus 1 over x squared minus 5x plus 6, right? So again, we are multiplying this first fraction times this quadratic trinomial on top and bottom in order to create this fraction right here. And that lets us add these together because these two denominators are the same. This is how you add rational expressions together. So this is going to equal x squared minus 5x plus 6 times the square root of 7x plus 2 plus 1 over x squared, oh, we don't need parentheses there, x squared plus 5x plus 6. All right, now it looks like we're going to be able to cross these out, but keep in mind we can't. All right, that's because in order to reduce a rational expression, you got to factor it first, and there's no GCF or anything here that will factor. So we can leave it like this. All right, looks like this thing can be left alone, just like that. So this is our function. Let's find the domain of this function. Now, what kind of function is this? First thing that this function is that we can spot is, first thing is that it's a rational function. And remember the rule of a rational function, x squared plus 5x plus 6, which is the denominator of this function, it cannot equal 0. So let's figure out where we're going to see some restrictions there. X plus 3, x plus 2 cannot equal 0. That means x plus 3 cannot equal 0. And on the flip side, x plus 2 cannot equal 0 either. So x cannot equal negative 3. X cannot equal negative 2. And this is the domain based on this being a rational function. But again, this rational function has in here that I'm circling, this is a radical. Right? This is a radical which is carrying its own domain. So the domain of the radical portion, remember how to find the domain of a radical function, we take the radicand, 7x plus 2, and we set it greater than or equal to 0. So subtract 2 from both sides. 7x is greater than or equal to negative 2. And then we can solve this inequality by dividing 7. And we get x is greater than or equal to negative 2 over 7. So we have 3 sets of restrictions here, right? X cannot equal negative 3, it cannot equal negative 2, and it also has to be greater than or equal to negative 2 over 7. So let's take a look at what this is going to be on how this is going to look on a number line. Right, let's put our critical values. Let's see, we have negative 2. Oh, sorry, the first critical value we have, reading from left to right, is actually negative 3. Oh no, I messed up somewhere. This says x squared minus 5x plus 6. So if you are watching this video and yelling at the screen, how come it turned into a plus 5x? You are not wrong. I am wrong. We are changing this, the denominator, x squared minus 5x plus 6. x minus 3, x minus 2 cannot equal 0. That means x minus 3 cannot equal 0. That means x is equal to 3. And that means over here, x minus 2 not equal to 0 means x is not equal to 2. Those are our critical values. I am very sorry about that. This is x squared, yes. X squared minus 5x plus 6. I'm sorry about that. Okay, so our critical values now are negative 2 over 7. And then the number 2, and then the number 3. Right, so x cannot equal 2 or 3. Those will be open circles. X can equal negative 2 over 7 because it says greater than or equal to. And from here, right, from here, we are shading, since it says greater than or equal to, we're shading everything to the right. But keep in mind, since it can't equal 2 and it can't equal 3, then we have to go, we shade around those on our number line. So essentially what we are doing here is, I'll draw this again to illustrate a point, is we're combining two different domains, right? Again, the domain for the rational function, let's put that one in green. The domain for the rational function is this: everything except for the number 2 and except for the number 3. So that means everything around there, towards negative infinity, towards positive infinity. Now in, let's say, orange, I will shade in this domain, which is x is greater than or equal to negative 2 over 7. That means starting from negative 2 over 7, shade this in. And then we'll shade in everything to the right of that. So like we said about any overlapping domains, our true domain is going to be only the part that overlaps, right? Since this end over here only satisfies one of these domains, that means it's no good. And since these 2 points here, 2 and 3, only satisfy one of the domains, those are not good either. But anywhere we see, in this case, orange and green shaded in, like negative 2 over 7, including up to 2, and then from 2 to 3, remember those points in between here, 2.5, 2.7, those are valid also. Union, 3 to infinity. This is the domain for our added function, h plus g. So notice that we had to look at the domain of this radical function and the domain of this rational function and essentially combine them together. Let's look at another. Same h and same g, but this time we'll look at h on top and g on bottom, right? This will be, instead of h plus g of x that we are going to find the domain of, we're going to find the domain of h over g, right? A divided function, h divided by g essentially. Right, so this means that 7x plus 2, the radical, divided by 1 over x squared minus 5x plus 6. Looking here at a complex fraction. So radical 7x plus 2 over 1 times the reciprocal of the denominator, which will be x squared minus 5x plus 6 over 1. So this function actually, even though it looks like a rational function, h divided by g, actually becomes x squared minus 5x plus 6 times the square root of 7x plus 2. So there's no denominators here, right? There is a radical, but remember, in order to find the domain of an operated function, something that is the result of an operation, you do have to take into account the original two functions that make up this new one, right? Because essentially here, since this is a rational function, g of x is a rational function, it's going to have some restrictions. Essentially, x cannot equal 2 and x cannot equal 3. So even though this is not in the denominator anymore, in order for this to happen, the values of 2 and 3 were never valid in the first place, which means they cannot kind of carry through to this new function, right? So that's why when we are looking at the function of h over g, we are looking at the function of the radical, which we did in the previous example, turned out to be x is greater than or equal to negative 2 over 7. And then we're looking also at the function g, which is a rational function, which again had its limitations of x cannot equal 2, x cannot equal 3. So if we combine these two functions, we're going to get the same domain that we had before, negative 2 over 7 is included, moving upwards towards infinity, but excluding the values of 2 and 3. So this is going to have the same, and then we would also have to find the domain using this radical, which turns out to be the same as this one. So we don't have to do that double work. But if this radical does turn out to be different, then you do have to find that separately, right? So again, negative 2 over 7 up to 2, union 2 to 3, union 3 to infinity. All right, so again, interval notation, building it and writing down all the intervals from left to right. So part 2c, let's look at this function here, g over h. Let's see how this differs from before, if it differs at all. All right, well, let's go through the exercise. G on top this time, that's going to be 1 over x squared minus 5x plus 6 over the radical 7x plus 2. Another complex fraction, so 1 over x squared minus 5x plus 6 times this reciprocal, which is 1 over radical 7x plus 2. So this becomes x squared minus 5x plus 6 times radical 7x plus 2 in the denominator, where on top is simply just 1 times 1. So a similar looking function, but all this stuff now is in the denominator. So remember, our radical function had a domain of x is greater than or equal to negative 2 over 7, right? All values greater than or equal to negative 2 over 7. Our radical function, that's the domain of g of x, right? I can actually call these the domain of h and the domain of g. This one cannot equal 2, cannot equal 3. Now, does anything differ because now this is in the denominator? It kind of does. Because remember, our new function, g over h, has this x squared minus 5x plus 6, which cannot equal 0. And it also has radical 7x plus 2, which cannot equal 0 because they're in the denominator. And in addition to that, 7x plus 2 must be greater than or equal to 0. So if we look at these two in combination with each other, this essentially means that 7x plus 2 has to be strictly greater than 0. Right? Again, This is slightly different than what we do with radicals, but because this radical is in the denominator, that means this radicand is strictly greater than 0. So if we take this, and 7x is greater than -2, divide by 7. Oop, there we go. I put that greater than or equal to by a habit. -2 over 7. X is strictly greater than -2 over 7. And from here, we work this out already. X cannot equal 2. X cannot equal 3. So let's look at a number line here. Very similar to what we had before, which is this critical value, -2 over 7. This critical value 2. This critical value of 3. This time, we are not shading in any of these circles. Why? Because x is now strictly greater than -2 over 7. Again, to repeat that, normally we set a radicand greater than or equal to 0, just like this. But because this radical is in the denominator, 7x plus 2 is going to get set strictly greater than 0 this time. So let's make some space for me here to write out in interval notation our answer. That's going to be -2 over 7 to 2, union 2 to 3, union 3 to infinity. And notice that our -2 over 7 endpoint is a round bracket this time, because it is greater than, not greater than or equal to. So I hope this helped. Look for the next lesson on composition of functions.